Hello again, and welcome back to my computer vision series. Today we are going to talk about denoising Detr, or DN Detr for short. So this is the map of object detection models that we have right now. So the current state of the art is CoDetr, and we are really just building up our way towards it. The previous state of the art is called Dino, and it was quite a famous model, and it was state of the art for quite some time. And in my previous video, I also talked about the Detr itself and the variants such as deformable Detr, DAB Detr, and today Denoising Detr. So all of those are actually a big part of the current state of the art. So these techniques are additive, and using all of them in your model makes it even better. And here is just the comparison to a more classical algorithm like YOLO. And I also have a video about that. So currently, denoising Detr is still behind YOLO in terms of the actual accuracy in object detection. But after replacing the backbone with a huge transformer model, and after making some adjustments to the algorithm, so Dino is based on denoising Detr, and it improves on the techniques that we'll discuss today, that already becomes much more accurate than classical object detection models. So here's the plan for today. So first, we're going to discuss why we need query denoising, why we think it's a good idea to research that topic even, and what is the fundamental problem we're trying to solve. Then we will go through denoising of the bounding box. We will go through label denoising, and finally discuss the attention mask that we need to use in the actual decoder. And finally, we'll discuss the results and what's next. Okay, so what is the motivation behind query denoising? This is the reminder of how the original Detr model works. So we start with an image, we feed that into the backbone, then flatten it out and add some positional embeddings to provide the network with the information about the position, which is lost during flattening. Then we pass it through a transformer encoder, which is just a self-attention, a few self-attention layers, and they receive this flattened sequence of image pixels, basically, and output the same flattened sequence, but more refined, more processed. Then that is passed on to the decoder. And from the beginning of the decoder, we start with object queries, which in DAB Detr are dynamic anchor boxes. So the actual 4 numbers for coordinates and size of the boxes that we are trying to predict, like the priors for the boxes. And then the output is basically 300 predictions, which are then matched to ground truth objects using bipartite matching laws. So some of those objects will get matched to a real object on the picture, but most of those 300 will not be matched to anything, and that will be just no object. So if we look back a little bit on the models that we've discussed before, deformable Detr focuses on the transformer, so how the actual attention mechanism works and how to make it more effective. DAB Detr looked closely on object queries, reformulating them and using the actual anchor box priors for these object queries that are not dependent on the image, instead of just random vectors with unspecified meaning. And now the denoising Detr is going to focus on this part. So what exactly is happening during bipartite matching loss and how we can make it better. So what are the problems with this? So let's say we have 300 network predictions, and we actually look at this image with 2 birds. So exactly 2 of these 300 predictions will get matched to the bird object. So they will receive some feedback for classification. So for classification, the backpropagating gradient will modify the weights of the network in such a way as to increase the probability that it assigns to the bird and make it closer to 1. and then decrease the probability that it assigns to other classes. And it will also receive some feedback regarding the actual bounding box coordinates of this bird. Most of the outputs, however, will be matched to the special noObject class. So this class the feedback that we get will be 1 for noObject, which will increase the probability of the network, the assigned probability to this special class, and then 0 for all the other classes. And in addition, we don't get any bounding box coordinates. We just don't use that in loss at all. So we get no feedback whatsoever. Now, the problem can be when the assignment is unstable. Let's say that we have two experts that are quite good at predicting birds in this upper left corner of the image. Only one of them will actually get matched to the bird. The second one, even though it could have had quite a nice prediction, quite close to the truth, it will be assigned to noObject, which is identical to saying that you shouldn't have detected a bird there. Instead, you should have detected nothing. And this also means that that expert does not get any feedback about how good the bird prediction was. So when you get assigned to noObject, even if you were really close to detecting a real object, but someone has done that before you, you get no feedback about what you're trying to do. And that might work. And the primary reason we need that is to have the network that does not output any duplicates. But this is really unfortunate if the assignment is unstable. So if on one epoch, the writer expert got assigned to the bird, then the left expert didn't know anything. It didn't receive any feedback about how close it was to the bird. But then if on the next epoch, the left expert gets assigned to the bird, that's unfortunate because it didn't have that much information. It didn't really train that well to detect this bird. But now we're telling it that it should have detected the bird. And the previous expert that might have done a good job at detecting, again, does not receive any feedback. So to sum up, problem number 1 is that only just a few queries out of 300 get any sort of useful feedback about where the object is. So most of them just get no object assignment and no bounding box coordinates to as a feedback. Second, the assignment isn't stable, and the authors of the paper actually demonstrated that it isn't stable. So if we go to the paper itself, so to the left, we see the assignments of the classical DAB Detr. So the arrow here shows where the center of the bounding box was, and the arrow shows where it got assigned to which object it got assigned to. And we can see that a lot of these arrows are actually quite long, which means that even though we hoped that the query input, the anchor box that we have as a prior, should match more or less the object that it is trying to detect, this is not what happens, at least not all the time. And sometimes you would get an anchor box prior somewhere here that in fact is detecting an object here. And then a couple of iterations later, the same object will get detected by a different anchor box, which really creates this confusing signal to the network, which is primary reason why it takes so long to train. So if we recall algorithms like YOLO, they take roughly 10 to 20 epochs on COCO dataset just to train in full. And the original Detr took 10 times that much. And that got improved a little bit after the deformable Detr and the DAB Detr, but it's still far behind the classical detectors. And the primary reason we think that is because of this sparse, inconsistent feedback that we get from this unstable matching in the bipartite matching loss. Another thing I wanted to mention is what the query prediction actually depends on. So it's not like 300 query predictions are completely independent on each other. Instead, they depend on what we call a content, which in the DAB Detr is just 0, initialized as 0, and the anchor box prior. So we have 300 independent anchor box priors that do not depend on the actual image. And also, it depends on the decoder weights. But decoder weights do not really distinguish different queries. Instead, if we look at the decoder, like here, the processing that happens to this query and to this query actually uses the same self-attention weights, the same weights to project that down to query key and value, to perform self-attention, to perform cross-attention, and so on. So the decoder receives this list of queries that it doesn't know how to differ and just performs this attention mechanism without knowing that they actually differ. So now, as we understand the fundamental problem of bipartite matching loss, so the instability of assignment and the sparsity of signal, let's discuss the solution. And we start with the bounding box denoising. So this is the diagram for that. So in white on the left here, we see the classical DAB Detr. So we basically start with DAB Detr as a starting point because it already has this query formulation as anchor box prior that we really need right now. So quick reminder how that works. So this is the decoder layer. So from the right here, we get the output of the encoder with the actual refined image content. And then at the bottom here, we have 300 white queries that perform the same way they did in the DAB Detr, where we add target to anchor box priors. And in DAB Detr, target was just initialized as 0 in the first layer, and then it is the decoder layer output for second layer and so on. And anchor boxes are the actual trainable priors for the bounding boxes. Now, usually in DAB Detr, we have these initial queries. We pass them through a series of self-attention and cross-attention layers. And the output of that is the same set of 300 queries. And we feed that into bipartite matching loss. So now what we do in Denoising Detr is that on top of these normal queries defined in such a way, we also have this special denoising queries. So denoising queries is a special task that is only present during training. So during inference, we will have no denoising queries. So the inference part is actually exactly the same as for DAB Detr. Denoising query is based on the actual ground truth object in that image. So in our case, we had two birds, so two objects, and we have a fixed parameterized number of groups that we want to feed into as denoising queries. And usually that's equal to 5. So out of 5 groups and 2 birds, we'll have 10 artificial queries. And so the target for them is the same for now. And instead of anchor boxes, we get noised bounding box coordinates. So we have our initial bird, and we know bounding boxes for that. We add some noise to it to make sure that we don't just tell the model where the bird is. And we then let the model perform the denoising task. So the model receives a query with some noise added to the bounding box. And then that specific query is always matched to exactly the same bird in the output. So there is no bipartite matching loss. There is total stability in how the matching is performed. And now we ask the network to remove the noise. So here is the original bird. Here is what you received as an input with some noise added. Please denoise that. And denoising loss is basically just the same as we do for predicting bounding boxes. So L1, IOU, so intersection over union, just basically how far the bounding box that we predicted is to the ground truth. And the primary reason why we think this is a good idea is that these tasks are actually quite similar. So normal DAB Detr receives anchor boxes that should be good priors for the objects we're trying to detect. And then in normal DAB Detr, decoder tries to see that the object is actually here. And so you need to adjust the bounding box prediction to better match the actual ground truth. And in the denoising task, we do something similar. So we also receive this bounding box, but now instead of getting that from the fixed anchor, we get that just by adding noise to the original bounding box. And we also ask the decoder to have this approximate location and to adjust that to actually point to the object. So the task being solved for these queries and for these queries is actually really close. And thanks for that. So once again, decoder does not really understand that the queries are different. It just sees a bunch of queries connected to the loss somehow. And by solving this task, this yellow part of the image, it helps to train the decoder to solve this task as well. And this is really the primary insight of this algorithm. So to sum up, initially we had 300 normal queries formulated as just anchor box prior inputs, and we add that 10 denoising queries that actually depend on the ground truth object. So normal queries have target, which is a 0 for the first layer, and anchor box priors. Normal query outputs are passed to bipartite matching loss during training, which is unstable. It might create contradictory signal, and the signal overall is sparse, but we still need that because we don't want the final model to output duplicates. Our denoising queries, the 10 denoising queries, consists of the same target, zeros initially, and noised ground truth boxes. And so this task of getting anchor box and adjusting that to point to the object, or getting noised bounding box and again adjusting that to point to the object, are really similar, which helps use one task to solve the other task. Denoising query outputs are passed directly to reconstruction loss, which guarantees that the connection is stable, so there is no instability inherent to it. And it actually improves the training thanks to getting more signal per image as well. So now if we originally had 300 queries, 2 objects, so only 2 of the 300 outputs got some useful signal. Now we have these 5 denoising groups, and each of them will get the signal, exactly the signal that we're trying to predict. And finally, we actually add an extra indicator feature to the target, which just says that 0 stands for normal query and 1 stands for denoising query. So actually do let decoder know which query comes from where, but thanks to the fact that they actually seem to solve similar problem, we hope that instead of having just independent pieces of the network solving one and the other, they will actually help each other. So learning to solve this denoising task will actually help the decoder to solve the original object detection task as well. And finally, during inference, we just don't have denoising queries. We just cut off that 10 query that we used to pass before. And the model works exactly as DAB Detr, but now it is trained better. So think of this denoising task as an extra crutch to help you train. And then once you trained, you just throw it all away and the inference code is exactly the same. And so results of that is that the loss itself is simpler. So we don't have this instability in bipartite matching loss. We just have original noised box, bounding box. We have ground truth bounding box. They are connected directly to each other, and that's just simpler and no instability. We get more signal per image. So instead of just 2 objects in the bird case, we get 2 objects for the normal version and then extra 10 objects for the denoising version. And the tasks themselves are similar, which allows us to use one task to improve training on the other task. Okay, so we have this cool helper task called bounding box denoising that helps us detect the actual objects. But we also need to classify the object. So can we have something similar that would also help with the label task? And turns out that we have, but not exactly. So we can also do label denoising in the following way. So we also have these normal queries and noise queries. So noise queries have the noisy bounding box coordinates, which works really well. And now we also replace the content part that we pass to the query. So before we had just target that was initialized at 0, and now we want to have some embedding that represents the class. So the normal queries will always have some unknown class. So this like the fixed embedding that doesn't correspond to anything that we can actually encounter in the dataset. And then the noised query will sometimes have the true label of the class with 80% probability actually. And with 20% probability, it will have the noised class. So just randomly flipped class, so just random class basically. And we, for the loss, we just use the cross entropy, the classical cross entropy or focal loss. So we get some class as an input, which is almost always true, but sometimes it isn't. And then we learn to output the correct class. So this helps decoder do the classification. And this is still quite a challenging task because you need to understand when it was flipped or not. So we had our target part, which stands for content. And in DAB Detr, that's just zeros. And we replaced that with class embeddings. So we now have 92 classes. So we have a known object that is always used in the actual queries that are used in inference. We have no object and then 90 classes from the actual Coco dataset. So person, bird, pizza, train, and so on. And we basically have a unique embedding vector assigned to each of these classes, and we train that. So normal queries always receive a known object as an embedding. Denoising queries receive the true class label that is flipped to the random class with 20% probability. This means that the task is now slightly different between denoising and normal queries. So normal queries always receive this unknown object class that is always different to what we're trying to predict, whereas denoising queries sometimes receive just the true class of the object, and sometimes they receive a randomly flipped class. So the tasks are now slightly different, but as experiments show, they still help improve the overall training of the model. Another important concept that we need to discuss is the attention mask. So normally in object detection models, we don't really use attention masks. So we allow every piece of image, every query to attend to everything else. Unlike, for example, text models that might want to predict what comes in the text afterwards. And to work as ChatGPT, for example, we cannot allow the model to look ahead in the future because during inference, the future is unavailable. And now we need something similar because we have our normal queries that do not really receive any extra information about image. They just start with the anchor boxes that are like priors that are independent of the image itself. But we also have these denoising groups that do receive ground truth bounding boxes, even though the noise was added to them. But something with noise added is still better than nothing. And if we would allow all the parts of the model, all the queries to attend to everything else, then the true matching part that is then used during inference might just get some useful information from the denoising groups, like the approximate bounding boxes, for example, and that information will not be available during inference time. So we want to fix that. So we want to fix the fact that normal queries might get some spoilers from denoising queries. We might also have the same between different groups. So if the first group receives this bird with the first version of noise, and the second group receives this bird with the second version of noise, just looking at different variations of noise of the same picture might allow you to easier determine what the noise is and what is the ground truth objects. So we want to isolate all the denoising groups as well. So, and for that we use attention mask. So attention mask is the Boolean mask, basically of true and false values, that tells you for each query where am I allowed to pay attention to. And so the first group is allowed to pay attention to other queries within the first group, as well as the normal matching part. Similarly, the second group and so on is allowed to attend to itself and to the normal matching part, but not to the first group, because it contains a different version of the noise. I don't want to provide that information. And the normal matching part is not allowed to attend to anything but itself. So it's not allowed to look into these noised bounding boxes because they will not be available at inference time. So this was it regarding the actual algorithm. Now let's discuss the results. First of all, and I love images like this, it trains faster and it achieves better result than the previous model, the DAB Detr in our case. So here we see the result on top of the original DAB Detr, but both of these models, DAB Detr and DN Detr, are also very well combined with deformable Detr, and that achieves even better results. Here's an interesting one. So we were talking about the distance between the anchor and the target. And as we can see from the left image, so the left image corresponds to the original DAB Detr. They don't always match, which means that sometimes an anchor that is supposed to detect object somewhere here is often matched to object somewhere here. And this is really weird because the anchor actually controls a lot of aspects of cross attention and the attention prior that we have and the area where the model basically focuses on. But just by creating the secondary task that really just gets some sort of noise anchor box and learns to adjust it to point to the true object, we also help with the anchor box matching to make sure that if we have this anchor box, it will be matched to something really close to it. And we can see that the average length of these arrows decreases in the Detr. And here's the graph that demonstrated better, I think. So this is just the L1 distance from anchor to the target in DAB Detr compared to the DN Detr. And we can see that the distance just goes down. So by showing this secondary task, suddenly the decoder just has this aha moment that, oh, I was actually supposed to detect an object that is close to the original anchor box. And as soon as it has this aha moment, it can actually perform better in its main task. This achieves 2% multi-average precision, both in the original DAB Detr and the combination with the deformable attention. This is no inference cost, and not that much training cost, so almost no overhead. So basically, the model at inference time is completely the same. We just modify the training a little bit. It combines well with other improvements like deformable attention, like replacing our ResNet CNN backbone with huge transformers like Vision Transformer or Swing. This concept of denoising is further improved in Dino, which takes the same concept and improves it a little bit. And Dino is quite a famous model. It was state-of-the-art for quite some time. And in current state-of-the-art, the CoDeter, we also use similar techniques. I also want to spend a moment to advertise what else do I have on my channel. So in the last few months, I was focused on object detection, starting with just the description of the task, the metric, and the dataset that we have, then going through a classical object detector called YOLO and reading the code for that. And this is my thing. I like to deep dive into the actual implementation, Usually it is much more complex than what you might see in tutorials and so on, so it's really important to be able to do that. Then I explain the actual Detr, the first transformer-based model for object detection, a deformable Detr, DAB Detr, and now DN Detr. And the very next video will be about reading the source code for DN Detr. Then we'll discuss the backbones that we might have to replace the CNN and the ResNet that we have at the moment, and that is VIT transformer and swing transformer. Both of these are then required to understand what is happening in Dyno model and Detr model as well. So Detr model is the current state of the art, so this is my goal for the next few videos to build our way to that. In addition, I have a more beginner content. So it's also about computer vision, about image recognition, but you can treat it as simply a deep learning introduction. So it starts with something really simple, digital classification with low resolution images. That's basically a quick start tutorial in PyTorch that you can just sit down, code in half an hour and understand everything that is going on. And then on top of that, we throw in a lot of concepts like convolutions, activation functions, parameter initialization, optimizers, momentum, weight decay, learning rate scheduling, and so on and so forth, that basically build the good foundation for deep learning and any area you might use that later on, like working with text, working with audio, image generation, and so on. And that results in the final project, which is to reintroduce the benchmark and to read the source code for the famous ResNet model that won the ImageNet competition in 2015. So it was famous because it was one of the first to beat human level performance on image recognition, and it is still widely used as a backbone for models like DN Detr, like we talked about today. In addition, I've started a new branch about generative AI and image generation. The first video is already out and it is about neural style transfer, but I want to go through more advanced topics like autoencoders, variational autoencoders, diffusion, stable diffusion, image generation conditioned on text prompt, and so on. So we have a lot to cover. I hope to see you again and see you soon.